With me later on, Collins will be joining in. I think he's already joined in. Hello?
Hi, Steve. Yes, we can hear you.
Oh, yes. Okay. Yeah, so my name, like I said, my name is Steve. I'm the senior geospatial engineer within Amini. Before Amini, I worked on remote sensing projects and basically Earth observation projects with different organizations. I was with NASA on an Earth observation program since the year 2016 before I joined Amini in 2023. Yeah. So what I'll be showing you today is one of the training manuals that we had whenever we were doing capacity development to different stakeholders and individuals on introduction to remote sensing. And then later on, we'll be showing you where to source Earth observation data from, which Collins will take you through. Yeah. So I guess we just get over and get started. Okay.
I just want
So I
to
hope
interrupt
yeah.
quickly. If you have any questions, please put them in the chat, and then whenever Steve breaks for a Q&A, we will answer your questions. So just type them in the chat so we don't forget them. Back to you, Steve.
Okay. So today we're going to briefly look into what remote sensing is. I hope you're all able to see my screen. There are some topics that we're going to cover. Some of them will go through them briefly, but then for the rest, I will try as much as possible so that you guys get to understand what remote sensing is. So to begin with, what remote sensing is. Currently, all of you are looking at your screen, either your phone or your laptop. You are able to get information from just looking at your screen. Your ears are able to get information just from listening to me speaking without physical contact. So the science of getting information without physical contact is what remote sensing is. Think about your remote controller device on whenever you control your TV. That is also a form of remote sensing. Think about your camera, your handheld camera or your phone when you take photos of a specific location. That is remote sensing. So whenever you're getting information without physical contact from any object or any activity or any repetitive activity without any physical contact, that is what remote sensing is. Okay, so that is in a nutshell. So for Earth observation data, this is the process of getting now information from features or physical features of the Earth, of the planet, or even of the planet without direct contact. So it's not that you are taking a sensor like a thermometer to go and check the temperature directly on a specific body, but then getting information directly from without physical contact of the feature or the phenomenon that you're actually observing. Okay. So for Earth observation, what we rely on mostly whenever we do remote sensing is on electromagnetic radiation, which primarily comes from the sun. All stars, the sun is a star, all stars actually produce electromagnetic radiation. And this electromagnetic radiation interacts with different objects on its path. So, for example, from our sun, light, this electromagnetic radiation, when it interfaces with objects on its path, it can either be reflected, or it can be absorbed, or it can be radiated. It can be radiated in different ways. Say, for example, for reflection, you'd see it directly, like when you're walking out in the sun, you'll be able to see an object. Sorry.
Abake, come back here.
Okay. Sorry about that interruption. Yeah. So yeah, like I said, the electromagnetic radiation that actually comes from these stars interact with different objects, and as I mentioned earlier, they can either be reflected, absorbed, or emitted by the objects. In as much as we are talking about Earth observation, think of remote sensing. Think of this source of the electromagnetic radiation as it interacts with very many objects. Think about it. You are able to detect meteorites if you are using Earth observation telescopes, because radiation from it, the visible part of the radiation reflects off of that body, and then you're able to see it. Every single time you go out at night and then you are able to spot a planet in the sky, it's because light from our sun, which is the closest star to us, reflects off from these different bodies, and then we are able to observe it on this side. So the same remote sensing is all about using that property, the property that electromagnetic radiation can either be reflected, absorbed, or emitted from the body the body that is on its pathway, and that reflected the energy that is reflected back with your eyes. What are you able to do? You're able to see. Whenever you walk outside at night, even during the daytime, or actually during the daytime, and then you see a tree, it's because the segment of visible light from the electromagnetic radiation. Don't worry about this term electromagnetic radiation. We'll be able to see closely in the next slides what it actually entails. But then just have this grasp at the back of your head that it's about the science of electromagnetic radiation interacts with an object. That energy is reflected back or emitted from that object, and then our eyes are are one of the natural sensors we have within our body, which are able to observe. But then we can also have devices that you interact with, devices that you have all around us, like your camera, your microphone right now, that is like the microphone on my laptop right now that is listening to me speaking. We have devices that have sensors that are able to capture that section of the reflected or the emitted electromagnetic radiation, and then convert it into a signal that we are able to analyze and decipher to find out exactly what type of object it is that we are observing. Take your phone, for example. I usually like to use very simple examples. Your phone, when you take a picture of an object, and then you go, after you've taken the picture, the first thing you do is go and look at what type of photo you've taken or what type of video you've recorded. You are relying on whatever source of light, where light is just a section of the electromagnetic radiation that has been captured and then stored on your device. The device interprets that and creates the images that you actually see. It processes it into the images that you've actually captured from such kind of devices. So within Earth observation, we have satellites that are airborne satellites. Apart from just satellites, we can also have IoT devices, which wouldn't be part of what we're going to cover here, but I just wanted to know that that is also another source by which you can get information without direct physical contact with the object that you're observing. Say, for example, you have a camera, a security camera. Let's just talk about very practical stuff. You have a security camera in the front of your door, or at a section of your house, and you're able to look at and monitor the situation around your building. That is a form of also remote sensing. So when we're looking at the Earth itself, then that's Earth observation. So we have satellites. You can either have satellites being carried by instruments, either on an aeroplane. There are times when we have sensors that are carried by an aeroplane, like cameras. And then we also have satellites that orbit around the planet that also capture radiated capture emitted and reflected electromagnetic radiation, and from looking at the property and the qualities of and the characteristics of the kind of okay, sorry. Looking at the properties and characteristics of the and the amount of energy that has been captured, the quality of the quality of the amount of the energy that has been captured back by these sensors, you are able to decipher and detect and discern certain things. The simplest one that I'll give out is, say for example, you just got there's a crowd that is before you and somebody is wearing a red shirt. You'll notice that if very many people are wearing blue shirts, or there's an array of shirts, people are like, there's a large crowd of people and people are wearing different color of clothing, you'll be able to detect the person. I know some of you might have realized that when somebody wears red, they are the easiest to spot. And it's actually that red color that you see it quicker than the person who's wearing blue, or somebody who's wearing uh, some violet color or colors around that side. So there's actually a reason behind that. And that's why I was talking about the properties. So there are different properties to the different wavelengths. Let me call them energy levels within the electromagnetic spectrum. I just want to be as simple as possible when I define this. So on the image that you see before you, you're able to see a wide range of the electromagnetic spectrum and the associated different frequencies and wavelengths for the different sections of the electromagnetic spectrum. So you can see that there are there are devices that have been listed at the bottom. For example, at the bottom left, you see the AM radio, and then we go to the FM towers, cell phone signals, your microwave, your body heat, which is actually interesting. I want you to try and think about some of these things. Think about what you can see with your eyes and what you can't actually see with your eyes. And then you have your remote control, the one that you usually press against your telly and stuff. Then we have visible light. We have sunburns. We have medical x-rays, and then we have a nuclear power station. You'll notice that all these elements, all these different energy levels distributed within the electromagnetic spectrum have varying wavelengths and have varying frequencies. Some of them are visible to you, especially the part where you see the visible light. Every single thing that your eye captures is only within a very narrow section of the electromagnetic spectrum. So you can imagine you can't see AM radio waves. You're not able to see X-rays. When you hear that a place is radioactive, we all know that, and we've seen that in movies, that guys actually go with devices, with sensors, to go and detect whether there's whether there's a radiation spill or something of the sort. But then our eyes cannot even see. Think about it, the simplest of things. If I told you that that cup is hot, and you're just looking at it with your eyes, you would like, your eyes will not be able to tell you that that cup is actually hot or the cup is not hot. So that means our eyes are not able to see into that section of the electromagnetic spectrum which concerns with temperature. We are not able to spot temperature directly, which is a very interesting phenomenon, and we shall look at how we use remote sensing to discern objects based off on stuff like that. There are those that reflect off a lot of heat, and then there are those that absorb a lot of heat, and we'll be able to look at how that property enables us to discern and to be able to identify objects that are visible within Earth observation data. Okay, so at the top you can see visible light with the colors of the rainbow. I know that everyone is familiar with that. So the white light that you usually see, or the light that you usually see, is the white light is composed of sections of the electromagnetic spectrum that have frequencies that are just within that narrow range, and that is what our eye can see. This every single thing you see, in as much as we feel that we are not blind, look at how tiny the segment of what it is that our eyes can actually capture is. It's a very small section. This is the only section that we are able to see. But then the electromagnetic spectrum actually stretches very far and wide with frequencies that span from almost 100 meters to picometers on the other side. And what we are able to see is just a very small, narrow range between infrared and ultraviolet. Okay, and we'll be able to see how this type of qualities actually influence what it is that we see and observe. Let me take us back to some common examples, like the one that I just mentioned earlier. Why is it easier to spot? I just wanted to understand how the wavelengths are reducing from left to right, and why the frequencies are increasing from right to left. So at the top where you see hertz, that's the frequency, and then at the bottom the meters, that's the wavelength. For those who did physics at one point, maybe you'd be able to know the difference between the two. So the reason why you are able to spot somebody who's wearing a red shirt easily within a room, a group of people, is you'll notice when you look at the visible light at the top, you notice that the red side of the rainbow is on the left. You notice that it's on the left, the reddish side. When you're moving towards the reddish side, you can see yellow, then orange, then red on the left. And then on the right of the visible light, you'll see that now we are going towards the purple side, from blue to I think magenta. Not so sure about these colors. I just think it's violet. Yes, towards the violet side. Yeah. So the reason why you're able to see somebody's eyes, who's wearing a red or a red object within your space, your field of vision, faster, is because if you look at how wavelengths are changing. Wavelength is inversely proportional to frequency. You'll notice that the red section of the light comes quicker to you. It has a much faster frequency than the purple side or the bluish side. That is why our eyes naturally detect objects that are red faster than objects that are blue within some space. Then there's another phenomenon that I can also explain on. Why is it that in the evening, when you look on a hill that is in the far distance, that hill looks blue? If you notice, if you ever walked in the evening and then looked, or in the evening, or just try and look at some land that is very far away, almost like the hills that are in the image that is below the images on the below the devices and the images, you'll notice that whenever you look at hills that are far away, they appear sort of blue. Then you wonder, why is it that objects that are very far away have a bluish hue rather than had they been red? It could be a red thing, or there could be a house with a red roof on a hill that's very far away. But then when you observe, you'll only see blue coming from that section. It's because the wavelength of the sides towards blue are longer, they are shorter. The wavelengths are shorter, so they come in. Remember, it's inverse proportional. So red comes quicker to you. The frequency is high, the wavelength is lower. But blue, the frequency is lower, but the wavelength is longer. So energy propagation, as energy is moving from very far away, most of the blue sections of the electromagnetic spectrum are what reaches your eye. That's why most objects from far away look blue. So that side of physics And that side of science is what enables us to actually do and carry out remote sensing. Okay, so there's a property that you'll notice with most of this. With I just explained a natural phenomenal property, but then I had to explain from the point of view of objects that are within your surrounding currently. On here, you can see a graph that is plotting the percentage reflectance, how much reflectance is coming off from different objects versus the wavelength, the value at each wavelength for the amount of reflectance that they give off. You can see the different objects. You can see snow and ice. Let's just talk briefly about snow and ice. If I ask everyone what color is snow, if you were to look, let's say, at a satellite image or to look at a mountain, and I asked you, what's at the top of that mountain? The first thing you'll tell me is that white part is snow. Why is it that we are considering that white part to be snow? It's white, it's bright because it's reflecting off a lot of light. That's a quality that I want you to just remember. It's reflecting off so much of the visible light across the entire visible electromagnetic spectrum, and that is why it appears white.
Careful, you're sharing your Slack.
Okay. Oh, sorry. I just saw. Did you write a message to me?
No, I wrote to Charlotte, but continue. You're doing great.
Okay. Sorry. Yeah. So like I was mentioning earlier, when you look at the top, when you look at snow and ice on an image or even with your own eyes, you notice that it's white, it appears white. And as you see the graph, from the graph, it shows that across the entire wavelength of visible light, so from around 400 nanometers to around 800 nanometers, you can see that snow and ice have the highest percentage reflectance across all the different elements, all the different sections of the electromagnetic wave between 400 and 800 nanometers. So think of it like this. Let me just go back to this image. Sorry for taking you guys back a little back. Visible light is white, but then its components can be broken down into the colors that we all see. When you combine all the colors of what we all see, that's what creates the white light that we usually see. When something is white, it means it's reflecting off all the sections of the visible lights are landing on it, and it's reflecting off all of them evenly. That's why it appears bright white. If I sit next to a shirt that is green, that means white light is landing on it, but then green is being reflected back to my eyes. All the others are being absorbed, but green is being reflected back. Okay, so based off on that property, we can see that ice from 400 nanometers to 800 nanometers and snow are bright throughout. In contrast with an item like, let's look at clear water. If I asked you to look at clear water, if I take a photo of a glass that is filled perfectly to the brim of clear water, it's going to be hard for some people to even decipher that that's actually an empty glass, or even think of air and clear water. It's because the sections that it's reflecting off are very low. It does not reflect off, it doesn't have the quality to reflect off a specific section of the visible light. So for example, think of a bottle of soda. If you look at a bottle of soda, because it's no longer clear and you can see it, that means it's reflecting off a section of the electromagnetic wavelength back to your eyes, and that's why you're able to see it. But then clear water doesn't reflect off much because light passes through it. It's transparent, so light passes through it. That's why you can see it has a very low percent reflectance. But then we have a very interesting phenomenon on this graph. I want you guys to look at the vegetation, and I'd like to explain that in a way in which you guys will be able to explain remote sensing to a 5-year-old if you wanted to. Think of all these plants that you see out there. Think of the tree that is just near your house, or a tree that you've seen. The trees have leaves, yes? When you walk in the sun, what happens to your skin? You sweat, right? You sweat. It's a mechanism that is built into you to try and balance your body temperature. You sweat to cool down your body. But then the tree doesn't go into a shade. It does not walk to a shade. It just stays outside there in the sun. It's always outside there in the sun. And I'm sure one of you, actually, every single person here has ever either touched a blade of grass in the sun or touched a leaf in the sun. What do you realize when you touch that leaf? Strangely enough, for a very healthy plant, the leaf is cold. How is it that that tree stands outside in the sun, but then when you touch its leaves, it's not hot as you. The leaves don't sweat. You've never seen leaves sweat. They just stay in that state under the sun, getting heated by all that by the infrared section of the sun, but then it remains cool. So leaves have a special property. They have a special property. They have adopted to the fact that they will always be. They'll have periods of time when they are under the hot rays of the hot sun. So what they've adopted to is can be seen in this graph. If you can see the graph, you can notice that the yellow, the broadleaf vegetation and the needleleaf vegetation behave almost the same. And snow and ice clouds are white because remember the property I told you, they reflect off most of the light that they disperse off and reflect off evenly across the entire visible spectrum of what they see. But then the leaves, you'll notice that for vegetation, the reflections, percentage reflectors goes up, then it reaches a certain peak, and then it goes down, then it goes up again. So there's a section of the electromagnetic spectrum where leaves reflect high. You can see on this graph it's around 600 nanometers. And then around, let's say 700 nanometers, it is very low. Then it goes up towards 800. So remember what I just mentioned. Leaves need a mechanism to actually maintain their temperature. They need a mechanism to maintain their temperature. The point where you see the leaf, the value of the leaf has gone, is reflecting off the highest. Where it's reflecting off the highest, that is heat. It's something which I remember, as I told you, if I told you to differentiate between a hot cup and a cold cup without the use of a special camera or special infrared camera or infrared sensor. I think now you guys are starting to get where I'm going with. Infrared is the component of heat is usually the infrared part of the electromagnetic spectrum. So that section of the infrared is where the plants reflect off the highest. So around 600 nanometers, it reflects off all the heat that is coming from the sun and landing on those leaves. The leaves have a special layer where they reflect it all away so that they can maintain their temperature. That's why when you touch it, the leaf is cold. So a quick question: if I gave you glasses, eyeglasses that had infrared, like let's say infrared eyeglasses, and I told you to look at snow, and I told you to compare by looking at a tree in the sun, where will it be the brightest? Just think about it. It's a very simple thing. Remember, infrared is the segment of the electromagnetic spectrum where heat is actually where we experience heat, where temperature increase occurs, which our eyes can't see. But then if I gave you infrared, trees are going to appear very bright. The tree that you've been seeing as green, if I give you infrared glasses during the sun, you're going to see that tree shining. Our normal eyes can't see heat, so it's hard for us to see. But then all the light, all the infrared part all the infrared part of the electromagnetic spectrum that lands on that leaf is reflected off. It's reflected off, it's reflected away. And then it reflects off that part. But then we remember from biology that, from science and biology, that leaves carry out photosynthesis. So there is a segment of the visible light of the electromagnetic spectrum which assists in photosynthesis. That is the red section. Do you see, if you look at the graph, the part where it's going down, that means it's absorbing that part. That is the section that it is not reflecting off that segment. So around 700 nanometers, you can see that it goes down to the lowest point, then it starts to pick up. This section where it's the lowest, that's the part that it absorbs to carry out photosynthesis, so that we have chemical energy that enables us to even attend this meeting right now. Because of this part, this lower part of the vegetation graph is what is keeping us alive currently. This is where all the energy is absorbed by these plants, and then they create chemical energy that is propagated to the rest of life. So what have we basically been talking about when we talk about these different elements? What we are looking at, these properties that we are looking at right now, is called the spectral signatures. So when you look at different objects, you are able to notice that they have different spectral signatures on how they react, how they behave with different levels of different segments of the electromagnetic spectrum. So you are able to tell, if somebody gives me a graph, if all these labels that are on the left, assuming I just have one line at the top, a line that looks yellow like this, and and just one line at the bottom, it's easy for you, who has not practiced remote sensing, to look at, who has just learned this, and we haven't even taken even 30 minutes. Can you imagine? In less than 30 minutes, you are able to discern what object you might be looking at based off on how it behaves on this graph, on the spectral reflectance graph. So that property, this property that we're speaking about, is what I say, this is the core of remote sensing. Say you are in a country where you want to detect minerals, you want to detect where gold is in your country, and you are able to study quite well the soil that is associated with where gold or diamonds or cobalt is found. If you are able to study that well and know the exact spectral reflectance of that soil, you can build a model that can detect any mineral you wanted on the entire planet. That is the beauty of remote sensing. Remember, getting information about an object without physical contact, looking at the qualities and characteristics of how different objects behave along the electromagnetic spectrum, enough for you to classify them as, this is what I believe this should be a plant. I think whatever it is that is doing this must be very bright. It must be an object that is reflecting off all the light. This other object is not reflecting so much light. It's either transparent, transparent, or it's absorbing segment. It's absorbing some elements within that. Okay. Also, a bit of a point of correction. I just realized something. So this middle part, that is being reflected off, because green, if you remember from this graph, the red part, the infrared part, infrared is on this side. The infrared part is what is being reflected at the middle. Sorry, here at the middle. Infrared is being reflected off a lot. The red parts of this graph are being absorbed, which is pretty much, yes. The infrared is being reflected off. So I was correct. It's not a point of correction. Infrared is being reflected off. Red is being absorbed. Okay. And then when you look at this graph, if infrared is here and red is here, what do you have on this side? Can you see that green is towards the middle? This section, this segment where it goes up high, can you see that the needle leaf vegetation has very few leaves, but broadleaf vegetation has so many leaves. So as we move towards the green side, every single time you see a plant that is green, you'll notice that if you look at the graph, these are log scale. Log scale, you guys could go and read up on the difference of the axis. So for log scale, you are multiplying in powers of 10. So just moving from one segment to the other segment, these are very large number. This is not just subtracting. This is not a linear scale. It's a log scale. So you can see the sides that it goes towards green are reflected off very highly, and that's why you are able to tell that this is a plant, this is a tree, because the light, the part of the visible light that is being reflected off the most is the green light. That's why your normal eyes can just pick out that is green. But if you are able to wear different glasses, if I gave you glasses for infrared, you won't see this other segment, you'll just see this segment. You'll see that plants are very bright. You will see this part. Think of you guys in the if you've ever gone out in the sun, some of you usually wear goggles called out sunshades. Sorry, am I audible?
Yes, you
Amy?
are, Steve. Steve, I just want to make you aware of the time and to give Colin some time as well. He's here with us. But yes, we can hear you.
Okay. So yeah, okay, we are squeezed for time. But usually this type of session, whenever I do introduction to remote sensing, it's good that I've at least given you, imparted a lot of knowledge to you guys. But usually this training takes a week. For like what we are doing today in 1 hour usually takes a week and I've done it all around. I worked with different countries in Africa, so I did it. This training used to take a week, but I've at least given you the concept behind what it is that we are doing. So this is what, remember when I explained about plants, that's what this slide is talking about, the same logic. For water, the same logic, based off on what is absorbed, what is reflected back, which section is being reflected back. So this is just interaction of different objects with how they react with this electromagnetic spectrum. Something else to also notice, a very important part of the remote sensing is how these different electromagnetic spectrums behave when they are transmitted or propagated through the atmosphere. If you go out when it's very cloudy and it's in the morning, you won't see the sun. Why? Because they have blocked they've blocked the sun out, and you're not able to even see the sky and stuff. So always remember that interaction, the way this electromagnetic spectrum pass through the air, there are different um, different 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 physical properties that actually happen, different events. It can either be reflected, it can be absorbed, it can be refracted. And so in remote sensing, there's an entire section of how you remove the effects of the atmosphere from these images so that you are able to see uh, the values, the spectral values, the reflected spectral values, the spectral radiance at the surface of the earth. Okay, so this is just an example of two different remote sensing products. One showing NDVI, which Collins will show you later shortly, where it's high and low. NDVI is just a measure that takes into consideration the characteristics that plants absorb the red part of the electromagnetic spectrum and reflect off the near infrared part. So it's just a calculation which looks at that property, and with it you can see parts of the world, of the globe, that are green actually have high NDVI, and then parts like around the Sahel region, northern Sahel region, you'll notice that have low NDVI. Okay. You can also be able to see ocean chlorophyll concentration, which can also be, it's also calculated through remote sensing, through different formulas, looking at those different properties. And chlorophyll actually gives you an indication for where fish is, if you want to know at any time. Okay. So as I said, the satellites capture this. This is very important, but then we're running out of time. I don't know what to do, Amy. Do I proceed because this is important? Okay, just know that different satellites, just like your camera, your phone camera, have different characteristics. It can be either the spatial resolution. You can imagine taking a picture with your Nokia, your old Nokia phone versus your iPhone right now. So we are looking at the quality. So that's like the amount of detail that is captured within each pixel. That's your spatial resolution. Temporal resolution is talking about the revisit time. How long does it take for a specific sensor to pass over the same place that you are looking at again? Let's say you are monitoring a hurricane. How long will it take before the same sensor is above the same location? But then for weather satellites, they are geostationary, and it's part of this. But then we'll not look into it right now. Just know that temporal is looking at the time. Spectral is looking at the range of wavelengths that can be captured by your sensor device. For example, you can have one that only takes red, some elements of yellow, and some elements of blue, so that's just 3 channels. But then you can have those that take in a very narrow range. So they have within red, it splits red within, let's say, 0.5 nanometer range. So you'd have very many images that can be captured with the same sensor. Okay. So this is just what I was talking about orbits. This is the placement of where these satellites are in space, like in height where they are. This is another one. We'll share this so that you guys can be able to see. Because of time, okay, this one is important. So passive sensors rely on an external source of electromagnetic radiation, like our sun. Like your camera is a passive sensor. But when you turn on the flash, when you're taking a picture at night, it turns into an active sensor because it's the one that is producing light, and then you're taking a picture of something in the dark, and then it's capturing back the reflected light off of that. So there are sensors like this one, like LiDAR, radar. Whenever you have radar, it's always a signal is sent out, reflected off whatever it is that you're observing, then reflected back to it. This is what I talked about, the spectral resolution. So you have multispectral, or you can have hyperspectral. So here you can have very many images captured within these ranges, but then here you have just a few. Spatial resolution, as you can see, this image is clearer, so it has high resolution. But then this other image isn't clear because it has low resolution. So that's the amount of detail that is captured within a specific pixel. I'll skip this one. It's okay. Temporal resolution, like I told you, the revisit time. How long does it take for a specific sensor to go back so that you can observe whatever it is that you wanted to see? Okay. Let's say, for example, it's a house that was being built. You want to see its progress. You might need to see it every month, or you might need to see it every day, depending on whatever it is that you're observing. Radiometric radiation resolution is how a sensor is able to discern between tiny fluctuations in energy to be able to discern objects. Okay. So for satellite data, there are different levels. There's, like, you remember when I said there's a level that can be captured with all the effects of the atmosphere not corrected, and then that can be transformed into a data product, like what you see on Google Maps. Whenever you guys are looking at locations on Google Maps, looking at the Earth or the satellite base map, they removed all the effects. You notice that you don't see clouds. You always wonder how comes there are clouds all around the world, but then you don't see clouds in those images. So there are processes that are done to it to get down to a level that is easy to use. Okay. I'll skip this one. It's more about projection. For projections, think of it this way: the world, the Earth, the planet looks something like this, but then you want to put it on a flat map. How do you transform something that, if I gave you a ball and told you to go and flatten it, imagine how hard that would be for you. So projections, all this doing CRS, coordinate reference projections, and all that is trying to transform parts of the planet into a planar view, and there are calculations around that. You'll be able to notice and know what different maps actually represent. The one that you use mostly is this cylindrical one. The one that you usually look on Google Maps, it's UTM. So this is how they made it. It's like they put a sheet of paper around the world, and then they traced the equator, and then did direct one by one from each latitude. They went and plotted out locations by that. But there are others. There's the conical and there's planar. Then I think for some of this I've already mentioned the advantage of this, because you are able to study very large areas and stuff. Let me just skip to the last one. The disadvantage of this is, like I mentioned earlier, remember that it's just like a camera. If you want quality, the price is higher. If you want like the temporal, if you want to monitor something daily, a satellite that will pass over the same location to monitor something for you, it might be too far. If it's free, the resolution will be off. But if it is commercial, then it's going to be expensive to actually get some of that data. And some of these data sets are very huge. Think about your phone running out of space because you've been recording HD videos. So now imagine a satellite that has been capturing very large data sets. So this data is usually huge. And there's a capacity, there's knowledge, there's a knowledge gap, that there's some knowledge that you actually need to be able to process and to deal with this data, or to even source it. And yeah, and the last one, we will still have to do validation for most of what it is that we say. You imagine a prospector tells you, show me the maps of gold, and then you're there, you quickly told them that this is where gold is, but you are not very certain about certain regions. You actually have to go and do ground validation for some of them. So thanks for that. Sorry that that took long. The introduction to remote sensing, the first basic class, is usually longer than 1 hour, but I hope Collins will be able to take you through various methods, various options to get Earth observation data. So all this data from the different satellites has already been collected, and it's being collected frequently from organizations that are using donor funds. Donor funds, and some of them are commercial, like what you usually see on Google Maps. That is commercial data, and it's expensive commercial data. Google usually pays for it so that you guys can get it for free, for everyone can get it for free. But it's usually expensive to actually get that data if you want it immediately or to study something. Okay, so Collins will quickly go through the different sources of where to get this data. But as he sets up, let me just stop sharing. As he sets up, Collins, are you there?
Yeah.
Okay. As he sets up, just know that you can go directly to the websites of the providers of the data to get that data directly, or you can use Google and different large data warehouse providers actually went and put that data within their ecosystem, and then they are providing it through different APIs. So Collins is just going to speak about one of the APIs, which is open source, which is called you can look up Spatial Temporal Asset Catalogs. He's just going to show you an example of one on how to get data. So thank you.
Thank you so much, Steve. I quickly want to interrupt before Colin starts. Steve, I don't know how you managed to whiz through about 1 year of study into one 20-minute presentation. That was quite impressive. I just want to let everyone know on the call that this is being recorded and it will be shared on Zindi. This webinar series is run in relation to the Amini Canopy or Crop Challenge, where you can go in. We've got those different bands of data, that the green, the red, they're named different things that Collins will be going through with us. Why are they named weirdly when they could just be called them red? That's a question for someone else. But please do sign up for the challenge. If we don't answer one of your questions here, we'll definitely answer it on the challenge page. This notebook that Collins is sharing, as well as Steve's slides, will be on the Zindi website on this competition. And just remember, if you attend all 3 webinars, you do get a chance to have a call with either Steve, Collins, or someone at Zindi. So see you at the next one as well. Over to you, Collins.
Okay, I hope you can see my screen.
Yes, we can see and hear you. Thank you.
Awesome. So this is like a very basic introduction to where you can find data, play with it. And for this part, we just use an open form of data sets that is usually stored in the cloud. I think it's in AWS. And it's using open standards to share the data. And for that particular case, it's usually the Stack APIs. So for this particular section, we're just going to look into how to search datasets using the search Stack API and then compute like a very basic index, which is common, the NDVI that Steve had just shown. And then how maybe to turn this data into a data frame, which might be useful, especially if you are a data science person. So here we're just going to like, these are just some of the libraries that you might need for this particular sort of application. This is the Stack library, which is the PyStack, and then you have Rasterio, you have GeoPandas, which is a common library for handling vector datasets. And this is like PyProj, Matplotlib, I think is very common, NumPy. I think these two I shouldn't have put them because they're already usually there in the collab. Yeah, so, and then we just do some importations. This is something that is put in by Google just to make sure that you're able to run some leaf map. And then now, this is element 84. Element 84 provides like images or those images for free. And it has a couple of them. So if you go into Stack Element 84, their actual website, you will see that they have like a number of data sets. So another interesting part, so I know there is usually in geospatial data sets, we have 2 forms of data sets. That is the raster data and the vector data. So in this particular regard, we need vector data to be able to search for for a location. So we just want to set our location where we want to get this data for, so that we don't get data for the entire world. And in that case, usually it's a very interesting tool called geojson.io, where you can just go and create a feature. You can create a point, for example, and then you can copy this, or you can create a polygon. So it's like you want to create an area of interest. So this is where I got this area of interest. Try to make it smaller, and then I pasted it here. So the first thing is to get like the image collections. What sort of collections do we have? So think of collections as a group of images that have been put together. And in this case, once we run this script, we are able to see what sort of collections do we have in this particular Stack API that we are having from element 84. And in this case, we see we have Sentinel-2, pre-CL, L2A, there is COPDEM, there is NAIP, there is these Landsat, and Sentinel-2 LA. Sentinel-1 is also there. This is the GRDH component. And just to go quickly through it, so we want to find more about these particular collections. So we can check the name of that particular collection, which in this case is Sentinel-2, level 2A, and we want to find out what it is about. So we'll get some information about the information. You have like the name, the ID, the coverage, the instrument on board, etc., etc. And we can also check for a specific, aspect of that particular collection. So in this case, you have like, this is the items. So it's more or less, for those who have done programming, it's like accessing it through dot notation. So you just do dot items, and then you do dot keys. We are able to see what exactly do we have. In this case, these are the band names or the names of the
the different wavelengths that have been captured. I think Steve has done a very good job in explaining what exactly those are. And then, so in this case, usually the Stack API sort of looks at searches images using the coordinates of that particular location. But somehow the format in which we get from our GeoJSON.io is not that compliant. So the Stack API will need this part from the coordinates, the geometry part, up to this part. That is what it uses to do the searching of the images from the stack, this stack library. So what we do, I've just written a very short code just to handle that part and return the feature collection in the format that is compliant with what that library expects. So, and then we have the collections part, which is just defining the collection that we want. So in the first scenario, we're just going to search the entire world without specifying where exactly we want this image to be located. So you're not filtering. I've just done a small filter of limit. And if we do this search, we're getting like around 768 items. And these items that we get, we can also still investigate a specific item inside the collection. And so we can use the array, or for Python, it's list way of accessing a specific item in a collection, and we're able to see what exactly we get. And we can be able to check the different aspects of it, which is like the different stack extensions. We can see the geometry of that particular location. We can see the links, etc. So in this particular scenario, you can also inspect the date time for it. And you can also inspect the geometry aspect of it. So where exactly is that particular aspect of that particular image? So here it's like doing things twice. So I created a JSON header. It's like just how a feature collection is supposed to look like in the Geospatial format. And this, we try and put back this geometry to be almost the same way it was. Now here, we use leafmap to display that particular vector data into the map, which we can be able to see it. It's somewhere in Kenya. We have a couple of counties. If you're familiar with Kenya, you have Elgeyo Marakwet, Uasin Gishu, Nandi, Kakamega, Bungoma, etc. Next, we now get into looking at filtering using or querying the metadata. So we are using the time aspect of the, so you remember up here, I've actually been able to see the date time of a specific stack item, which is an image. And down here, we are trying to filter that particular stack. We're searching the stack using a date time. So we want just images for 1 month, which is 2021 of January to the end of January of 2021. If we do the search, okay, I am not a robot. What is this? What is it asking? Okay. I don't know if this is okay. Sorry about that. So we have 12 items. So we can still also filter with the cloud. So usually when you talk about remote sensing or Earth observation, we usually talk about noise. And part of the noise is actually cloud cover. But if you're interested in studying the clouds or how the cloud formation, the rain patterns, you might be interested in cloud. So you might even want to do an image that has higher clouds instead of an image that has low clouds. And then, so here if we do, for example, cloud cover, we end up with like 5 items. 5 items searched if we do less than 5% of cloud cover. We can also search using that feature collection. So in this case, we are using the feature collection we created. And this one, we are looking at where it intersects. So here you can use either a point or a polygon to look at where the images are intersecting. It is more or less a spatial operation, and then it will return for you all the images or the stack items that are inside that particular location. And so if we do that, we still remain with 5 items. I think it's also because of our aspect of cloud cover. And we can also group by. So here we did a query, and then we can also be able to check the cloud cover properties. So for each item, what is the percentage? So you see you have 0.1, 0.3, and then 3. Now, so here we can even be able to save this one into JSON that we might use later. So for that particular stack item, and it will go somewhere in our drive. And of course, we can still be able to check for that specific item, what exactly do we have in terms of bands, which we will be able to check here. And we can also find additional information about the bands. So this is exactly what Steve has been talking about, the variation in terms of the resolution for each band, and then also how many they are, and some additional information that you can get from this particular experimentation or exploration. So here we're going to look at how to visualize it. And this one exactly, we're able to get. So when you do like these particular explorations from the stack items, maybe for example, we go back to somewhere like here, we can be able to see the links, can be able to see, for example, the link where that data is, etc, etc. So if we go down where we had reached, we're able to query this thing using requests from Python and visualize it just the normal way you can visualize an image. This is a thumbnail. So a thumbnail is just used as a preview for that particular image and not the actual image. So it's good for, let's say, if you want to build an application that people are choosing images from, so you can be able to use that. Finally, we want to try and do a bit of computation of images, or even converting that image to a cloud optimized GeoTIFF. So we want to load this image into memory, and here we read the assets and we get the href, which is actually the link of that particular image. And then we can be able to see that it is in the format of xarray data array, and it has x. This is the y and x. These are just the pixels that you have. And so if you check, you will see additional information where you have and every other thing that you need. So at this point, we want to just visualize with different CMAP. CMAP is like a visualization color scheme that you might need to do that. And finally, we are able to do some visualization. I'm just cognizant of the time, so that's why I'm trying to get to where the bit is. And of course, this repository or collab notebook will be shared. So because the image is a bit big, so if you look at this image, this is covering a very huge area. If you're familiar with Kenya, this is Kakamega, and this is forgetting the name of these areas, but this is in the Rift Valley, and this is western part of Kenya. So this is a very huge image. So it might be difficult to load this image into memory, but of course there's techniques such as using Dask to do that. So in that case, we try and maybe look at the subset of this data. So of course, it's also still the same thing that you do with Python. So we're just doing some sort of subsetting of this data. We're taking like from this point to this point, and then from this point to this point for the X, so Y and X, and you're able to visualize this data. So finally, we go to computation of indices, which is the most important bit. So indices are used to do a few things. Most of you maybe might have heard of something called NDVI. It is a normalized difference vegetation index. It's used to check for the crop health of a specific vegetation. And you can even use it to do thresholding for generation of crop mask. You can use it to do thresholding for forests. And this can help you. So if you check a platform like Global Forest Watch, they are using this particular index to generate some of the forest layers that they use on that particular platform. And so what I want to do, because it will be computationally expensive to do it, we do a subset. And part of the pre-processing of satellite images, especially the Sentinel-2, we divide it by 10,000 so that we are able to get an image that is further processed. And then we apply the formula, which is near infrared minus red divided by near infrared plus red. And here we are able to visualize that image. So, first of all, we visualize the red band, the near infrared band, and finally we visualize the NDVI itself, which is supposed to range from -1 to 1. And those areas that are in red are supposed to be areas that are not performing well in terms of vegetation. And those areas in green are performing well. And this location in Kenya specifically is Uasin Gishu, is a crop-rich region. And it's in January, so you see that some of those fields or most of those fields are in the green part. So most likely it was off-season. It was off-season, and that is part of the reason why you will see like this forest appears darker, because these are like permanent vegetation and others are temporary vegetation. So here we can also be able to turn this into a data frame, and you can actually read that into a data frame. So finally, at the end of this particular presentation, we are looking at the next steps. So there is a format called X-array datasets, which basically you can be able to read multiple images and turn them into a task data frame, and you can use that for machine learning, you can use that for analysis, for anomaly detection, etc. So up to that point, I hope that we've been able to understand a few things about working with OpenStack. And also there is other sources of datasets that like Google App Engine, which is a tool that you can use to write code and also to explore some of these datasets. It has multiple datasets from different sources, including the satellite data, the climate datasets. It also has like some datasets in hydrology and a bit of datasets. So I don't know if there are questions, but I think this is where I finish my talk.
I would like to add one clarification. So you remember I told you guys, I told you earlier that these images are usually huge. The amount of memory that it takes to store an integer number is smaller than it takes to store a decimal number, a floating number. So when we do that division, so the satellite image itself, because it's very huge, the values are usually saved as either int6, unsigned integer 6, or unsigned integer 8, or integer 8 or integer 6 for those who done computer science. So when we divide by 10,000, we are bringing back the values. Remember that the reflectance values are in nanometers, so we are bringing them down to the range, to the surface reflectance value range, so that we are able to discern objects easily. Yeah, so that's why I was dividing by that part. And for NDVI, like I mentioned earlier, we're looking at vegetation. Remember the characteristic of vegetation that I mentioned earlier is that they absorb red and they reflect near infrared. So the formula that Collins has just shown up there, there's a formula. Yes. So this formula is for calculating this specific index, where we are looking at that difference in properties. So we are doing near infrared, we subtract red divided by near infrared plus red. That is a set formula for calculating that. And if you go down to NDVI at the bottom, at the very bottom, so the two bands that you saw up there, that's an image captured in near infrared. That's what the sensor picked up as near infrared. and the sensor, what the sensor picked up as red. Then when you carry out a calculation with them, this is the final end product. And you can see NDVI ranges from 1 to -1, where the parts that are very dark green on this image that you can see on here is where the vegetation values are high. Think about, just think, what is always green? Even if it gets dry, it's always green. You walk outside, this thing is always green. It's trees. It's a forest. Some forests always remain green all year round. And then in places where you have vegetation, where today you've planted something, tomorrow you harvested, it's the vegetation has gone, you've cleared the entire field, or the vegetation is very sparse because the plants are just starting to grow. Then you see that the NDVI values are low in certain places. In places where you have no vegetation, then near infrared is absorbed. Near infrared is absorbed. Like, let's say, for example, soil. When you touch hot soil, it feels hot, right? So it is absorbing some of it. That's why when you touch it, you can feel it. So for that calculation, then you get negative values when you do that calculation that you've seen on there. So that's why you can have negative values on NDVI, and for vegetation that reflects off near infrared, you have high values. So thank you I just wanted to clarify on that. So think about it, you're subtracting something near infrared minus red. So for it to become negative, it means red is higher than near infrared. And when red is higher than near infrared, that means it's something that you can see. Remember that in your eyes, we see the visible spectrum, so RGB. If what you are seeing is very it's discernible, like it's a rock, it's a piece of rock, then, or it's some color of soil or stuff like that, then it's some soil, then you'd know that the red is being reflected off a lot than the near infrared, maybe, that you can't see. You can see the soil better than if you touch it, maybe. So those type of properties are what we use to calculate to see some of that. So thanks. Sorry. Back to you, Collins and Amy.
Thank you, Steve, for that. Does anyone have any questions for Steve or Collins? I think we have time for one question for Steve and one question for Collins. You can raise your hand.
I've tried as much as possible to answer the ones that were written on the questions that were there on the charts towards my session.
Yes, I saw that. Thank you so much.
Okay.
Collins, do you mind if I take over sharing my screen, or does anyone want to ask any questions first? Yes, Dennis. Do you want to unmute yourself and ask your question? Dennis, go ahead and unmute yourself, please.
Hi, can you hear me? Sorry.
If you can speak a bit louder.
Can you hear me?
Yes.
Oh, okay. So thanks for that presentation. I think my question is, do we have like standardized NDVI values for, let's say, dense forest? Because this is usually a big challenge when you're trying to classify different land cover based on their NDVI values. I understand water is mostly negative values. So do we have like a standardized NDVI values for different crop cover or land cover?
Okay, so I can take that on. Two things. Remember, first when you mention NDVI, I want to just remember what I said about the properties that we look for. There are items that will be green throughout, like throughout the year. Perennial trees, your mango tree, maybe your avocado trees, dense forest will be green throughout the year, regardless of the season. So the NDVI values for those type of crops will always be high. So that's what Collins was mentioning about thresholding. Stuff that trees or a crop, land use, a cover, actually a land cover that has NDVI values that are high all year long, you'd expect that is a tree or that's a forest. Those are the kind of properties that we usually look at. But then when you want to, when you look at a time series of a specific piece of land and you notice that the NDVI peaks around one time, then it goes down, then it goes and picks up. It can either indicate that that is cropland where they've harvested, or it can also indicate that maybe if the NDVI was very high throughout the entire year, high through a couple of years, then the NDVI values go down. It can indicate deforestation, that there was a place where there used to be trees and the trees were cut. So there are different ways of looking at that. So here what I'm mentioning both. You can do thresholding to only find values that are around 0.7 and above, and you'd know that that is 0.7 and above through a time range, then that is a permanent forest, a dense forest. But then when you find values that fluctuate, so it's not just about looking at one image and saying, I want to classify this image because I know maize should have an NDVI value of around this. I answered somebody on the group. Think about, if you ever seen, okay, I don't know whether there's maize and sugarcane in your country, but if there's maize and sugarcane, these two plants look almost the same. Like if you looked at a satellite image, at one point of time, they will almost look the same. That is why, if you look at one of the disadvantages I said in remote sensing, is you have to do ground validation. So you will have, and people, now this is an area of research. People usually go, like there was a Zindi competition where the first Zindi competition we did, we collected land cover, ground sample truth for different crops. The basis for doing that was we want to go and look at the spectral signatures of these specific crops, find out using machine learning methods, like what makes them significant, either using just the bands that you've been Collins was showing, which are multispectral from Sentinel-2. That's just one of the satellite products, satellite products that we use. But then you can go deeper into the hyperspectral range, where even within the red section of the electromagnetic spectrum, you have more than one slice of the red band, and you have more than one slice of the near infrared band, and then you can carry out analysis using the NDVI calculation for all of that to find out how does maize behave where sugarcane is not behaving like this. And those are areas of research, active research. The other way, if you don't have all that, if you don't have hyperspectral data and you have ground truth data that you know that this is actually maize here, that's why we do land use land cover classification. People use random forests and stuff like that. But then if you know exactly what is at a specific location, then you can use the temporal classification aspect, which I just mentioned. If you know that these people only plant maize between this month and this month, and then when they harvest maize, maybe wheat is still growing in that region or something else is still growing in that region, then from that aspect, you'll be able to know when the NDVI values of a specific field have gone down, then you're able to infer on which crop it is that they've changed. So if you don't have so much, you can use the temporal aspect, the time aspect, to know this season, these people usually plant this. So if I found that NDVI values are high in some of these fields, then it's this. If the NDVI values are lower or increasing towards some time when you know that these guys have already harvested a specific crop, then you're able to know that these are different. That's a different crop or land cover type that you're looking at. If NDVI values are high through and throughout, highly likely you're looking at trees. Trees, even through dry seasons, most of them don't shed off all their leaves. They just remain green because their roots go all the way down to the water table. So that's why they always keep hydrated. So as I was mentioning, As I was mentioning, yeah, those different types of properties are what you can actually use to do that. The data that we got with Zindi, we are also looking at. We also looked at the growing date, the planting date, so that data can enable us to be able to do not just temporal classification, not just pixel-based classification by looking at surface reflectance values, manipulating spectral signatures, but also looking at the temporal aspect of these different land cover classes. Yeah, so thanks.
If I add something maybe shortly, so what happens is that different forests will behave differently. There are those ones that will shed trees. So if you're looking at tropical forests, especially tropical rainforests, which are evergreen, then you can do with the thresholding values of 0.7 and above. You can also include additional indices like Advanced Vegetation Index, Bare Soil Index, and do something like a PCA for that. We tried something like that for 5 countries in East Africa, and it actually worked. And then we are able to generate like a vegetation index based tree cover. So over to you. I hope we have answered your question completely. Or yeah, awesome.
Thank you so much. My apologies. Thank you so much, Steve and Collins. I'm going to wrap up the webinar here, but I'm quickly going to share my screen. So we have the Amini Canopy or Crop Challenge on Zindi. So all you need to Google is Zindi Amini Canopy or Crop. Amini has amazingly used some of Collins's script to pull out different pixels. Someone's not on mute. Could you please mute yourself? Sorry. Amini has taken different pixels from around Africa. Some of these pixels are cocoa, some of these pixels are forest, and some of these pixels are palm trees. And this is quite interesting because we're using that NDVI, the Normal Distribution Vegetation Index, and those are all green trees. So how do you tell them apart? So that's the really difficult part of this challenge. But they've also got that time series that Steve mentioned. So can you see how the trees change color over the different seasons? They might not drop their leaves, but they might reduce some of that greenness or increase in some of that greenness. So that's an opportunity for you to play with the data. I want to show you a snapshot data, is that it is already in tabular format. And we here have the timestamps of when the satellite passed over. You can see it's almost every 5 days. My challenge to you on top of the Zindi challenge is, can you take these green, blue, and red, the near infrared, and can you plot some of those pictures that Collins was showing us? Can you find that NDVI index? Can you make it more green? Can you make it less green? And that information. You can find all the data on the data tab. I will be posting the recording of this session on this challenge page, so please do come look here. I want to mention the mentorship opportunity again. The first 20 users to attend all 3 webinars will get a one-on-one call with someone from Amini, such as Steve or Collins, or with someone from Zindi, who's an Earth observation specialist. So thank you to everyone who came to where and how to source observation data. Next, we'll be processing Earth observation data for machine learning to learn more about it.
Non. Surtout par la finale, ils sont sérieux.
Thank you so much for joining us today.
Mais on peut parler un carton.
Rose, I have many thoughts on NDVI and different types of density, but I can't tell you my answers. So I think this is a good question to ask on the discussion board. Great. Thank you everyone for joining. We will share this later.
Okay. Bye, everyone.